So that is a fiber, core is there, cladding is there, and you can go for kilometers to kilometers. But here, similar type of waveguide, but that is fabricated in a planar platform. So it is kind of so that you can integrate thousands of devices together to get a particular type of functions. So this type of ring resonator is one of these components. So these ring resonators can be used to generate single photon or entangled photon pairs. Okay, so once you generate, the next thing is to actually, you have to separate them from its source, noise, all those type of things. So you need a component where you can isolate, where you can separate these single photons or entangled photon pairs. So one of the structure I have shown here, it is called some kind of DBS structure, distributed Bragg structure. So I'll be explaining a little bit how it works. And the next thing is that once you isolate your photon, single photon, entangled photon pairs, etc., then you can actually use some kind of generic structure I have shown here. I think this fine white line you see, there are two lines coming together and going out there. They are two waveguides basically. And those two waveguides actually, they are interacting very closely in the central portion here if you see. And a little bit of zoomed version of that structure here shown here, that is actually nothing but this is two parallel waveguides separated by a gap. That is called directional coupler. So if your photons are coming from one of the inputs in the left and maybe in the both ports, and then they can interact each other, and then you can get certain kind of output here. So you can get certain input and it is kind of output things you will be getting here. So that is actually called action, or you can actually manipulate. You can just doing some kind of operating on single photon or entangled photon pair, and then you can measure by a photodetector to get the output functions. Okay, so this is the three basic things you need for integrated quantum photonics. And where they can be used, first thing is the communication systems. So communication, you know, that's optical fiber. Actually, what Professor Bhadra said that you are getting quoting cow that you will be getting telephone line almost free. Bandwidth is so large because of the fiber optics and optical communication systems. But one major problem is that nowadays, you know, whenever you are sending a data through optical channels, even that can be in the free space, in between, anyone can actually intercept the data and can decode your data. But that is actually possible. Even though you are using a lot of algorithms, you can make some complicated coding so that some security code, all those type of things. Nowadays you are getting, for example, whenever you are withdrawing some money in the bank, you are getting one-time password, that is actually security code. But those type of code is, you know, frequently you are hearing that they are being cracked and they are actually your money is gone from the bank account. But if you use this quantum nature of photon, entangled photon pair, etc., then you can actually get ultimate security, which is directly guaranteed by the laws of physics rather than by complex mathematical algorithms. Okay, so that is actually ultimate. No one can actually decode it. It's guaranteed completely. Physics says that. So you don't need to worry. So that is one thing you can achieve using your quantum photonics, integrated quantum photonics circuit. And the next huge things, actually, Professor Bhadra also mentioned a bit, high performance computing. So high performance computing is actually, you know, a lot of nowadays you can see that supercomputers, multi-core computers also even in your laptops, so that you can get faster computation and simulations and complicated problem solving, etc. you get. But quantum, if you use the quantum nature of the photon, you get actually quantum supremacy, offering unprecedented computational power. So you can do within a second a huge amount of calculation data you can generate, and you can sort it out, and you can also incorporate artificial intelligence and deep learning, all those type of algorithm you can use, and that's a huge things also there. Nowadays, you know, Google already developed quantum computer, and you can use that. They have used 50-qubit quantum computer, but problem is that they are using Josephson junction, which operates almost at 0 degree Kelvin temperature. So that's a huge, gigantic amount of machines and like a building size computer. But nevertheless, it is now open to all also. Even you can sit at your home and you can use that quantum computer if you just buy some license, software license from there. So that is also possible, but it is not completely, it's commercial yet, still it is development mode, and you cannot really scale it up. For example, that type of computer you cannot expect in your desktop, as your desktop. That is not possible. That's a problem, but it is still, at this point of time, that is actually a huge thing. And then third thing that is actually coming up, it is not yet explored much, but that is called quantum imaging and spectroscopy. So you can use the quantum nature of photon, and then you can get a high resolution of imaging of any structure that can be subsort noise. You know, noise is the killing factor for any type of imaging things. And another thing is that lithography. Lithography is, lithography very common for fabricating integrated circuit, electronic circuit, so that your transistor size nowadays in the order of 10 nanometer. So that 10 nanometer you cannot go down and down because of the technological limit, lithographic limit. Because lithography you do again by using your optics. Optics has a diffraction limit, lambda dependent. So, but if you are using your quantum photonics, quantum nature of the photon, then you can actually go to the atomic level lithography. But that is actually, it's a technology not is in the developing stage. So, with this background, this is the background that this is a huge prospects and a lot of investment going on. And I want to spare this time, actually utilize this time, just discussing about, for the wider audience, about photons and photonic qubit. Because photons, that means single photons and entangled photon pairs, they are used for communication system, security purpose. And then photonic qubit, qubit means quantum bit. Quantum bit, and that is actually used for quantum computations. Their fundamentals I will be discussing a bit. And then second thing is that quantum photonic integrated circuits. So how they are realized, how they are implemented. Basically, that is very easy. Once you understand photons and photonic qubit and you can generate, isolate and all these interference functions, you can do it. You can actually use existing technology platform. Photonic integrated circuit technology already commercialized, is in the market. You can directly access that technology and you can just design your circuit and you can get photonic function, quantum photonic functions. So all these type of things is possible, and some of the developments I will be discussing. And then, third thing I'll be just talking about recent progress at IIT Madras. As Bijoy was saying that I have started research here in IIT Madras since 2006. And all the years I was actually developing silicon photonics technology so that we have the indigenous fabrication facility and international standard fabrication facility we do have here. And since we are equipped with that, and last couple of years I'm busy in doing some sort of quantum circuits, quantum photonics research, and we have some grant also for that, and we'll be just discussing how far we are now. And then finally, I'll be just summary and some concluding remark. So these are the four different sections, and most part I will be just discussing about this first part, because that is the catch. Because once that is understood, I think you will feel that it's nothing difficult. And I will not go much deeper. And even if you don't know quantum mechanics also, I feel that you will be comfortable. I kept everything very easy level. So you don't need to worry about just listening about quantum and qubit, all those type of things. I just kept the things very easy. So with that, I just first try to discuss about what is the photons and quantum entangled photons, how qubits are generated. So as I said, that optics is well known, optical science, optical engineering well known, very long time. But photons, the history of photon actually starts exactly 1900, December 1900, when Max Planck actually explained the black body radiation. This is the figure here shown here. There are two curves. X-axis is frequency and y-axis is radiation intensity. So that time, if you just hot body, people started experimenting what type of spectrum, radiation spectrum coming out of that. And while explaining that, Rayleigh and Jeans came out with a formula. That is left side, if you see 8 pi nu square by CQ kVt, that is the thing. So that formula, from the physics point of view, classical physics point of view, explained, and it goes like this curve, like at lower frequency, radiation intensity will be very low, and as it increases, then it is suddenly the intensity will go up, and that is actually called ultraviolet catastrophe. But in practice, you don't see that. Experimental results does not show that actually. That ultraviolet catastrophe never happens. Rather, it happens like this, whatever it is, this type of curve is there. And no one could explain that time, what happening there. Then this Max Planck, he is a bit, actually expert in thermodynamics. He was actually just doing research on entropy, law of thermodynamics, all those type of things, and tried to explain this thing because it is black body radiation, heat radiation, all those related to thermodynamics. And then he actually modified that equation, and that modification could be achieved possible by thinking that at any frequency, the energy is actually, it's like coming like a quanta. Epsilon, 2 epsilon, 3 epsilon, and so on. But this epsilon not equal to 0. If epsilon equal to 0, that means we are considering continuous thing. So with this aspect, and he tried to fit the experimental results. And while experimenting, he has to introduce one constant, and that constant given symbolized as small h. And actually, this h was initially taken as a constant for Hilfgröße. You know, Hilfgröße, it is actually a German word. That means it is a help parameter. So, in other words, in good English, you can say that this is a fitting parameter. Okay. He thought that it is just a fitting parameter, and it is actually explaining, and a lot of people nowadays also, they do a lot of modeling, etc. They use several type of fitting parameters. Maybe some of them are having some physics basis is there, and some of them just consider, okay, you use this fitting parameter, then it gives your experimental result correctly modeling. So something like that. But that one later found that it is actually like a universal constant similar to like C and G and all this electronic charge, all the universal constant, and the value was also later it was measured as 6.626 into 10 to the minus 34 joules second. So, but that time he said that energy quantization concept used, but he himself never believed that really energy is being quantized like that. So it is one way of explanation according to him. Okay, so now another guy, another famous experimentalist, Philip Leonard. Actually, he was doing some cathode ray. He got Nobel Prize because of his cathode ray invention. So while he was doing cathode ray experiments, he found that if you just illuminate some light, UV light on a metal, and then some kind of electric current is being generated, and you can actually collect that electron, and you can really get current, good current. But he could not analyze because he is an experimentalist. Little bit weaker in theory. I would not say that weaker, but he could not explain that thing. So then Einstein, you know, that time he was mid-30 that time, and he was looking at the experimental results and this photoelectric effect and trying to explain with the Planck's concept of this age and nu, all this type of thing, because he had used the similar concept there to explain the heat capacity at low temperature in solids. So he was actually using that thing, and he found finally that, okay, actually photoelectrons are generated following this rule. That kinetic energy of the photoelectrons equal to half MeV square, where m is the electronic mass, velocity, and so on, and h nu is the quanta of energy, and that is the quanta of energy. It's coming out of electromagnetic wave from the light, and part of its energy actually spared just to remove the electron from the metal. That is called work function. So rest of the energy, entire energy, whole energy, you can actually get as a half MeV square. That is the maximum electron energy you can get, and that is actually depends on only frequency, that maximum velocity. Okay, that depends only on frequency, never depends on intensity of the light. So with that, actually he first time said that when light energy delivers or receives some electromagnetic wave, actually delivers some energy, deliver as a quanta. And when something coming out as electromagnetic wave, that is also coming out as a quantum. So that one, in German word, he started calling it as a least quanta. Least means in German word it's a light. So light quanta or energy quanta, as it was known that time. Okay, so that's all. 1905, he explained this thing, and I should remind you once again, Einstein got Nobel Prize because of this, for explanation of this photoelectric effect, not because of its celebrated E equal to mc square. Okay, so then you see, now given that he started saying that, okay, light is a composition of quanta of energy. Okay, then another interesting thing in 1909, while he was just explaining about the energy fluctuations in a certain cavity, and in his own words, it is just called whole round. Whole round means hollow space. And if in a hollow space, if you have a radiation inside, somehow it is because of the temperature or because of anything else, if you consider a sub-volume of small v, the part of bigger volume, and there if you try to analyze that what is the variance, energy fluctuations, that is actually this variance, actually epsilon e square bar, it is mentioned here, that fluctuation, energy density fluctuation we call it, has a two distinct part. First part you see h nu is there, and second part is, it is eta naught. Eta naught is nothing but the average energy in the sub-volume. And the second part is like that, c cube by 8 pi nu square for a particular frequency. Okay, and after deriving this, so he actually just mentioned that this is actually the first part coming out of the quantum nature of the photon, electromagnetic wave or radiation. And the second part is actually the contribution coming out of wave nature, because he has in his mind Maxwell's equations. He loved that Maxwell's equation so much that the wave nature is actually has to be there. And his theory also shows that part of it actually photon and another part actually wave. Okay, so the particle-like fluctuation comes comes from the spontaneous process of the radiation matter interactions. So that part actually happens spontaneously, and it is beyond anybody's control. That spontaneously can happen. Nature gives that. And the wavelength fluctuation, second term, that is stemming from the induced process. Induced process means what we call it as a today stimulated process, stimulated absorption or stimulated emission. That time he mentioned that as a absorption and negative absorption. That time gain was actually unknown, so negative absorption he mentioned. Okay, so with that, actually Einstein convinced that, okay, he mentioned that, okay, energy wave is there, and electromagnetic wave, inside electromagnetic, there will be some singular points where energy will be consolidated, that the energy packets, that is photon, and it is spreaded, the entire thing, the field will be varied. It is similar to like if any charge carrier is there and field will be generated, and that way wave will be something like that. He was just speculating that time, because he was in confused state, how it can happen, that quantum nature, wave nature, all those type of things. Actually, it's a Crompton, you know, I think that is also in school level, it is taught nowadays. So he actually experimentally showed that quantum of energy can be scattered by electron, another quantum particle. And it can actually elastically scattered, non-elastically scattered, it can give up some energy, and it can recoil in different directions. All those type of things can happen. So it is, he said that it is a particle. It is a particle, energy quanta is a particle, quantum particle. Okay, so the Compton's remark on the particle nature here, after his this theory proved experimentally, theoretically, he everything explained, and then the present you have energy, you have momentum. So that time also people are okay, but nevertheless, in the meantime, it is only in 1926, from 1900 to 1926, that time actually one chemist, American chemist Gilbert Lewis, he actually christened this least quantum, Einstein's least quantum, as a photon. But you see, interestingly, he mentioned a nice thing. Actually, you will love what he said, that I therefore take the liberty of proposing for this hypothetical new atom, which is not light, but plays an essential part in every process of radiation, the name photon. He said that it is an atom. And also he said that obviously it is not a wave, it is not electromagnetic wave, it is some kind of things, it is carried over by the photons. So I found this is a nice cartoon here. So am I an X-ray photon or a radio photon or visible? Oh hell, why worry about all that again? I'm not even sure if I am a wave or a particle. Photon now actually faced in a self-identity problem. What it is at all the things. So again, you see that Maxwell's in 1860 to 71, he actually demonstrated the celebrated equation, that's so-called 4 equations, Gauss law, Ampere circuital law, Faraday law, all this combined together. And that time the electromagnetic wave, the wave nature is actually celebrated that time. Everything, interference, refraction, everything could be explained. And suddenly this photon quantum nature is coming. How to club with that electromagnetic wave? All those type of things. Okay. Maxwell actually showed in 1865 that light is a transverse electromagnetic wave and it can propagate even in free space. Okay, and this plate you see here, just because of the success, IEEE actually made 3 plaques, and one up in his university and birthplace, and somewhere else 3 different places they have circulated. So actually, this, the electromagnetic wave, and based on that electromagnetic wave and maximum velocity of light, all those type of things, Einstein actually, his relativity came into picture, relativity theory. And basically, before that, no one used to say that Maxwell's equation. Just, okay, some equation, some paper he has published in 1865, and based on that electromagnetic theory can be explained and so on. But Einstein popularized the name Maxwell's equations. That 4 equation, here it is written here as you see, they are Maxwell's equation in 1940 while explaining his theory of relativity. So when Einstein was asked if he stood on the shoulders of Newton, that's a 16th century, he's a celebrated scientist and all-time favorite that time, he replied, no, on the shoulders of Maxwell's. So he was actually favoring more of Maxwell's than Einstein's, Newton's, all this discoveries earlier. So now, just 1 minute. Now, okay, all right. So now we see that you cannot actually rule out the wave nature, electromagnetic wave, all those type of things, what Maxwell says, and Einstein himself used them for his relativity, all those type of things, so you can rule out. But then later on, research went on, and here I just tried to very briefly, I want to say that how this wave nature and photon nature club together and being used today's everyday's life. So first thing is that you see electromagnetic field modes are equivalent to quantum harmonic oscillator. You see this is an electromagnetic wave, propagating electromagnetic wave in the x direction. Okay, source will be somewhere in at a distance. It can be free space, and you know that electric field and magnetic field, they are orthogonal, 90 degrees to each other, and all the energy will be propagating along the x direction because of the Poynting theorem. E cross h, all the energy will be flowing that direction, and it is shown it is a monochromatic. So you take in black body radiation all types of frequencies coming from say very low frequency to high frequency zone, and here if you see it's a one frequency only, and plane wave one frequency, and this one frequency, if it is traveling, you can just assume that as a kind of optical mode. So optical mode, if you just, this optical mode can be in a confined cavity also. And also it can be considered as the cavity can be infinitely extended. So this mode, it can be shown from the Maxwell's equations again, that it can be equivalent to a harmonic oscillator. Each of this mode, each frequency coming out of your black body radiation or wherever, so they can be considered, they can be shown that they can be acted as a just a quantum harmonic oscillator. What is quantum harmonic oscillator? you know it, just earlier also it's a harmonic oscillator. Professor Bhadra was saying that if you in a harmonic parabolic potential like an electron, if it is in a parabolic potential, and if you use Schrodinger wave equation and then solve, then you can find there are discrete energies, and that the particular state, nth state, the energy will be h cut omega n plus half. So that is the omega is the just characteristics frequency or so-called of the harmonic oscillator, resonance frequency of the harmonic oscillator. But when you say that each of these mode is equivalent to a harmonic oscillator, quantum harmonic oscillator, so you can say that quantum mechanically, particularly if you just use Heisenberg pictures, Dirac's picture, all those pictures if you solve, then you can find that each mode, you can solve energy for each mode, and that energy also will be similar nature because it is harmonic oscillator also. And there also in harmonic oscillator, you know, potential energy and kinetic energy, they are actually maximum potential energy happens and then kinetic energy maximum, and together it's conserved. Total energy is conserved. Here actually total energy conserved between electric field and magnetic field. Okay, so energy is shuttled back and forth from electric field to magnetic field. So same way you can actually make some analogy and you get this type of energy. And in that mode, you have a mode. Mode means frequency is constant. Omega is fixed. Now what is n? So this n is the photon number here. So in each mode, you can actually keep on increasing the number of photons. It can be infinite number. Each mode, depending on its intensity, mode number, photon number can be increased. But problem comes, suppose you have a cavity mode and monochromatic, you think, and you can take out all the photon one after another, somehow, some thought experiment you can think of. If you take out all the photons out, then what is left over? You can get, when n equal to 0, that means E equal to half h cut omega. That means that is called 0 point energy. What is that? Half of the photons. You can, photon cannot be actually broken out, no? You cannot make it into 2. So that's a problem. So what is that? And then it is shown that since it is an energy and it is an electromagnetic wave, and you can actually, this energy, if you just convert back to the equivalent electric field and magnetic field, and that will become like a complex type of field strength. That is called vacuum field strength. Okay, that's 0 point energy vacuum field strength. And since that is a complex, like a wave function or complex amplitude, and you can think that also follow Heisenberg's uncertainty principle. That means some fluctuation will happen. So position, momentum, all these type of fluctuations happens. And that vacuum field, if you just express this, if it is the mode is in a volume V, then vacuum fluctuations expression looks like this. Actually, you see, if V is very large, volume is very large, this vacuum fluctuation field strength will be relatively small because it is actually, see, 1 over V square root. So it is small. But whenever go to very small cavity resonator, V is small, this vacuum field will be large. And that can fluctuate also. It is something like that, the energy will be, this vacuum fluctuates someone actually more like that. Some phoners and disappear, generates and disappear all the time, something like that, that type of things happens. But overall energy will be like that. You cannot take out that photon, you cannot dissociate that photon, but that fluctuation can take place. But that vacuum field fluctuation is very, very important and responsible for all sorts of spontaneous transitions. When we talk about any transition, laser emission or something like that, we say it is spontaneously emitted. But that spontaneous emission, actually this vacuum field fluctuation is responsible. The vacuum field fluctuation actually disturbs the system, and that causes some kind of transition, spontaneous transition, and that we call, that is a spontaneous, that is a natural. Basically, that is it is a E vacuum is the responsible. Smaller the volume, V higher is the vacuum. So this vacuum fluctuation, all the spontaneous emission, that is responsible. Now, okay, now we understand that vacuum fluctuation that actually helps to have some kind of spontaneous emission, and also we understand that a mode you can have huge number of photons can be there, and number of photons you can increase, decrease depending on the strength of your oscillator, strength of your source, all those type of things. Now, next thing is that why I am discussing all this, because we want a single photon. because we want to use the single photon, that is a quantum particle, quantum nature I want to utilize. So how to extract a single photon? Single photon means it is not a single photon someone is giving in your hand. It is something like that. At any point, at any instant of time, only one photon will be there. And next instant of time, another photon will be there. But we know that photon is some kind of, it is a massless, it is a shapeless. In the same space, you can hundreds of photons, thousands, infinite number of photons you can just pack in. So, how to get a single photon at any point, at any instant of time, and that photon can be used, and its quantum behavior you can utilize for different type of functions. Okay, so that's actually a huge thing. One thing you can think, okay, laser was discovered in 1960. You can have a very good monochromatic intense laser source. Can we get a single photon out of a laser? Let us see, try to understand this. Okay, monochromatic light wave photon source. So you can say laser is a monochromatic light. Okay, so though it is not completely monochromatic, we can assume for the moment, for the sake, you can just figure out. And you assume that 1 nanowatt power is coming and laser is emitting 1550 nanometer wavelength, that is the communication band, fiber optic communication band. And for that band, laser, if photon is there at all, that energy if you calculate, each photon carrying energy of 0.8 electron volt. Now, this 1 nanowatt power, this is very, very little, that means 10 to the power minus 9 of a watt. That type of power level if you have, because you want to come down to the smaller amount of photon number. So if it is, the power is, the laser beam is going 1 nanowatt power, and if you see that velocity of light is 3 into 10 to the power 8 meter per second, and if you just think the length of 30 centimeter beam, if you consider, and that actually corresponding, if you just use velocity of light, that is a time of 1 nanosecond. So 1 nanosecond span, light can travel 30 centimeter. If you calculate, just you get from the velocity of light. So if you are trying to detect, your detector, you can actually detect 1 nanosecond long time and try to see how many number of photons, for example. Okay, you just calculate from the power known. Power means energy per unit time, right? Energy per unit time, how much energy is flowing, that is power. So from that energy, if this photon energy, if you divide, you can get number of photons. And on average, you will get, if 30 centimeter range, length, if you consider, there will be on an average 8 photons will be there. So 8 photons will be there means you can just think of their separation on an average 30 divided by 8. So about some 45 or some 4.5 centimeter or so. So every 4.5 centimeter you're supposed to get kind of photons. Okay, so that means if you just try to chop every 4.5 centimeter, you're supposed to get 1 photon. This is a simple calculation I have just shown here, but actually in practice you don't get that. What you get here is the, actually they follow certain kind of statistics. If you just see the thermal, you just take a black body radiation and you just consider one particular photon, a particular frequency, omega, okay? And then you just sample, so certain length you sample, each time you sample maybe 30 centimeter, a little more, so that you get on an average 10 photons. And 10 photons on an average. But if you keep on sampling each sample, and most of the time you see, this is x-axis, you see number of AN you are getting. First, I think the sample which is having not at all any photon, that will be the maximum probability for black body radiation. And then, as you see, increase the number of photon in each thing, the probability will be dropping. You see this thing, this type of nature, the exponential nature will be there, thermal things will be there. So that is a common, any thermal source, if you see, that is the distribution statistics you are getting. So there will be something, you see even 20 photons you can get in one sample. So you were thinking that, okay, every 4.5 centimeter if you chop, you're supposed to get 1 photon, but it can happen that there are 20 photons within that. So it's hardly will be getting a single photon by that point process. And if you see a laser, this highly monochromatic, intense everything, and it is actually coherent, stimulated emission takes place, all those type of things, and their statistics, laser statistics, photon statistics in each sample will be a little bit different. And that will follow Poissonian distribution. So I have just shown that's the first thermal distribution that is actually discovered by Bose-Einstein. Bose actually first he discovered and communicated to Einstein. All this story, you know that. And then the statistics, all this thing following this formula. And laser process, actually that follow the Poisson's distributions. But same 10 average photon, if you supposed to get in 30 centimeter or something centimeter length, you can see that each sample, if you just detect, sometimes you get most of the here you get a 0 probability 0, and then maximum probability you get 10 photon in every sample, and also you can get 15 also, sometimes you can get 5 also, you can get 20, even if you get 100 also sometimes comes. So those type of things, it is called some kind of photon bunching, all those type of things, that is not very good to isolate actual photon, single photon. So another type of classification of the source, light source, you can see based on the distribution, which are relative to the Poissonian distribution laser. So you see this is here in the right side, this photo shown here showing 100 average photon in a particular sample length. Okay, 100 average you should get, if you just average infinite number, then you can get 100. But if you see, if sample wise, if you just try to see 100 photons in distribution as I explained in the left side, but all the thermal and like LEDs, bulb, tube light, all those type of things, they will be not Poissonian, they will be spreaded over. So that is actually called super Poissonian. So those are actually very bad for isolating single photons because distribution is wide. But there are some kind of squeezed state of source you can actually fabricate or you can make, engineer, there you can get sub-Poissonian distribution. That means this standard deviation can be reduced from the Poissonian one. So in that case, you can get on an average, most of the time, every sample you can get a finite, narrower, you can actually predict, okay, this is the things. But that is also very difficult, I will explain a little later. Okay, so in this way, actually these are the limitations. So from the one thing I can make you sure that use simple laser, you keep on attenuating, we will never get a single photon. Sometimes it is punching and most of the time it is going like backend or something like that. Most of empty spaces will be there. So it is very bad. Actually, a lot of experiment also shown that it is coming like a single photon. Okay, it's very hard to get. And all right. Now I think my job is a little bit simpler here because Professor Bhadra already explained a little bit of nonlinearities, all those type of things. I will explain how, because there are many ways people demonstrated single photon source. Just single photon you can get out, for example, hydrogen atom. You know that the Lyman series, all those type of things, those photons are there, but normally you have to have, you can get a single photon, that is true. You can isolate them, that is fine, but you have to use them for some functions. Like an integrated circuit you want to use. You want to get some kind of function done out of it. So if it is in hydrogen atom, how you will put a hydrogen atom in a chip? That is very difficult. So if a lot of other sources are there, those are not really useful. But as you know, this I just explained earlier that this what you call that, this vacuum fluctuations, that is responsible for spontaneous spontaneous transitions. Here I have just tried to show that if you use a material which is nonlinear, suppose Chi2 means that is actually the nonlinear susceptibility is there, then what you can get, if you have some kind of intense laser light, monochromatic laser light, what happens, one pump photon, because of the Chi2 process, because of the light matter interactions, it can generate two daughter photons called signal and idler, and with a lower energy. But energy conservation is maintained. Pump photons equal to signal photon and idler photon, but they are lower energy. Total should be same. And that photon pair, they are occurring because of the Chi2 process spontaneously. And that spontaneously, it is not that when it will generate, that is for sure, but you can actually control that at a time, one pair of photon will be generated. And you can extract that pair of photon on demand. Because you can control your pump source and you can attenuate pump source. If at all generating, they will be generating in a pair. Okay, so that is how, and those two daughter photons, they are some way, they are entangled, they are correlated. Correlated means some function you will find, with that function you cannot actually distinguish any of the photons. The global function it will be there. Even though these photons are separated a large distance, but that relationship, that function is, they will be following a certain kind of wave function, that psi, whatever Schrodinger introduced and nicely presented by Professor Ghartok, and that global function is there actually. Okay, they are somehow related. So that entangled photon pairs more will be actually highlighted by Professor Anand Jha in next series. You will come to know, but they will give you some kind of entangled photon pair generation, and then you can actually, of course, you can separate them. Because they are two different frequencies, you can separate them, but they can be still correlated. You can keep them light years apart, but still they will be related. If you just somehow detect one of the photon, another photon will be existing there. Otherwise, they are together, combined. That is how entanglement we understand. There are two types of this type of spontaneous parametric down conversion. One is type 1, where signal and idler both are in same polarization. You know polarization, normally in a waveguide, horizontal polarization, you have vertical polarization. Okay, so if both signal and idler are in the same polarization, here it is written, horizontal signal, horizontal idler. This K notation is the wave function. Just this pair photon jointly we can express that horizontal signal, horizontal I. That is actually representing their polarization. Or they can be represented by vertical and vertical, V for vertical here. That is called type 1 type parametric down conversion, where entangled photon pairs will be generated. Now type 2, they will be actually signal and idler are always in orthogonal polarization. So this entangled state is that any pair you will be getting, if signal is horizontal, idler is vertical. Idler is vertical polarization. But when they are generated, they will be actually coming out like a combined state like this. So this is the global function. This is the entangled function psi, whatever I was talking. So once this is the two part will be there always. So if you can actually measure either this part, first part, or this first part, this second part, when you are measuring. So when you measure signal is horizontal, definitely your idler is vertical. Even if it is at a large distance, once you measure your signal, that is horizontal polarization, idler is vertical for sure. But you can, if you are just measuring this one, somehow you just somehow measure this one, then it will be entire wave function will be collapsed into this, and signal will be vertical, and idler will be horizontal. So at a far distance, far away distance, without any communication, no information, instantaneously you can say that, okay, now I got this is vertical polarization. Definitely, even that other photon large distance from me, that is definitely horizontal polarization. So that is the beauty of entanglement, and that beauty actually used for quantum communication, quantum key distribution, all those type of things. I will be just describing little while later. So another sort of things, for example, silicon. Silicon, we are using silicon photonics for optical interconnects, all those type of things. In silicon, that chi2 is absent because centrosymmetric. So again, if chi2 is not there, then you cannot get this. They are a spontaneous process. Their birth history is same. They are combined. Somehow they are related. So same thing also you can get type 1, type 2. But in case of silicon, it is mostly type 1 type. It happens. Okay. Now, so entangled photon pairs and heralded single photons. Now you see, you have entangled photon pairs. You can spare one photon. You detect. Then you can herald, you can see other photon existing, and you can use them for some certain functions. And that function, that wave pair generation function, you can express like a psi wave function with this equation in the box. That Cn, n, n. N is an integer, stands for signal, and second one is I, because they are generating always in pair. If n equal to 0 here, n equal to 0 here. If n equal to 1 here, n equal to 1 here. But they will be generating one photon pair or two photon pair, three photon pair, they will be generating with a certain kind of weightage. Probability, Cn will be their coefficient. That is a complex coefficient. That complex coefficient For both cases, SPDC, that means spontaneous parametric down conversion or spontaneous four-way mixing process. So that Cn can be expressed with this complex function, where this R is known as a squeeze parameter. That parameter actually depends on how much pump intensity you are using depending on that. Higher the pump pressure level, R is higher. If pump pressure level is low, R will be lower. So controlling R, you can actually control the function Cn, this complex coefficient Cn. So controlling that Cn, actually you can limit this Cn, this series, this is a series, it can be, first two terms can be relevant. Other terms can be, that means higher number of photon pair generation can be limited. So with that, first two term means sometimes no photons at all, and sometimes one pair of photon will be generated. And that can be very much well controlled with using your pump laser source. Okay. So in this way, you can actually get either no photon at all at any instant of time, or if it is generated, first coefficient that Cn equal to 1, that means one signal photon, one idler photon will be there. And then you can actually use one of them for detection purpose to herald the other one, so that you can use them for different type of functionalities. Alright, so far so good. So we have already single photon on chip, you can generate. I'll show some of the work ourselves we have done. I don't know I'm running out of time or not. Bijoy, you should remind me what is the time left. So I'm still a long way to go. I'm just halfway actually, I would say. So single photon, so we could isolate, that's fine. Now it is a quantum, no mass, energy, momentum, everything is there, polar, everything is there. Now, how to handle that? How to handle that? How to use them for different type of application? The most fundamental question for that type of application when it comes is the first figure if you see here. It's a figure A. It is, you see, a single photon coming in and you have a beam splitter. Beam splitter normally, it can be beam splitter, it can be polarization splitter also. I will explain that later. For the moment, it is beam splitter. Beam splitter means it can be 50-50. So 50% normally typically light comes, 50% goes this direction, upward direction, and 50% will be transmitted. It will be divided into two intensity, classically. But if single photon comes, what happens? Single photon cannot be divided. So whether it is coming this direction or this direction. So to know that, what you could do, you could put a photodetector here, or put both position photodetector. And it is found that sometimes photons are detected in one side and another side not there. Sometimes photons are detected there and sometimes photons are, when next photon coming there, it is not alternative, it is just for a probabilistically. That if, sometimes photon comes there, that probabilistic nature you can also define. So from there, actually, you can just recall what Professor Ghatak said, that this hidden variable. So sometimes people thought, actually when photons are being generated, that time its polarization already decided, that it's somehow decided it will go which direction. Polarization or direction it is decided, and that hidden variable. But that is not that is actually proved later. And Bell's theorem and then Alan Aspect's experiment, all those type of things that is proven that that is not there. So it is actually probabilistically coming. You don't know what things coming. But here you will see that when you are detecting in one side, it is somehow measure the photon existence missing from the other side. Quantum something goes here, it is reflecting back, and you see the interference here. That is actually Michelson interferometer, and you know all the optics things are there. Optics books you will be finding, and classically you will see that interference pattern depending on the phase difference between two mirrors. Path difference will see, depending on the phase, you can actually force photon with this similar classical way interference pattern you can see. That means, that suggests that it's some interference happening. That means the photon is actually simultaneously present in two paths, and they are actually related to the phase difference, and accordingly you are getting this interference pattern. So it is actually wave and particle. Here you can say that it is coming like a particle, and here you can see the wave-like nature. But nevertheless, need to know that a photon comes in a beam splitter, it presents in two paths, multiple paths it can present simultaneously. And those two paths, we can say that they are actually basis vectors. We can say that, okay, whatever things are there, we can define that with a complex function, say A, and another complex function B, and they can be considered as a eigenstate of the system, entire system, measurement system. Okay, so whenever these two eigenstates are there, then you can think of their superposition states can exist. Whenever incoming photon is there, you can think that then incoming photon can be represented by the psi, and the psi can have a superposition of A eigenstate and B eigenstate with a particular coefficient alpha beta. They can be complex because they can be phase related. And nevertheless, because photon you are considering this beam splitter is lossless, etc., this alpha square, beta square plus beta square should be 1. So that thing should be there. So it is just particle or wave nature of the photon depends on actually observer's detection measurement system. How you are measuring, depending on that, it is a wave or particle. Otherwise, you don't know. You cannot say photon is a particle. You cannot say it is a wave. It's something complex thing. Complex thing we express like a psi. But only thing is that depending on the measurement, we can try to find out what type of functionalities we can get. Okay, this is a quantum particle anyway. Okay, now single photon quantum state. We can say that their beam splitter I was talking. Now you just consider it is a polarization beam splitter. That means if your photon coming here, if it is a horizontal polarization, it should come to detector D2. And if it is a vertical polarization, it comes to this side. But if your incoming state, photon coming with a certain angle, neither horizontal nor vertical, with an angle, then we know that, okay, it is something like that. Where it will go then from beam splitter? It is the same situation like this earlier beam splitter. It is a polarization beam splitter. You never know, because here it can actually decompose into horizontal and vertical to basis vectors. But you are coming with a theta. A single photon. So which direction it will go? D1 or D2? Again, here you can express the psi as a cos theta vertical, sin theta horizontal. And probability of finding at D2, maybe this is cos theta term or vertical term. Vertical term in D1, it is cos square theta and sin square theta, and cos square theta plus sin square theta equal to 1. So quantum state of a photon we can just express into decompose into two basis vector or maybe two basis vectors to eigenstate. Their superposition, that is again a eigenstate also. They are pure states basically, pure state of a photon. So you can express like that. So how that is being utilized? Okay, this probability everything, how they are being utilized. So one is secure. I will be just superficially I will be explaining just for layman type things, understanding, hand waving things. There are much deeper understanding, mathematical derivations, all those type of things are there. But we don't need to go there. Just think here how this entanglement and this polarization single photon state being utilized for secure quantum communication. Classically, if you think, this is Alice, Bob, it's a foreign name though they're demonstrator like that. Alice and Bob, maybe they are communicating with optical fibers, optical channels. You are considering light pulses coming, 1010 digital data will be coming to your internet. Alice sending from his from our computer, Bob is receiving in his computer, and through fiber channel is coming, it can be mobile or etc. But in between, maybe there is a guy who wants to steal your data. Okay, that is actually called Eve. So Eve can do what you can do because it is a fiber line is there in between. So he can actually, she can actually just cut the fiber and splice that and a little bit tap it. Even if you just fiber, you know, a little bit. Yes. Even fiber, if you just remove your cladding, then evanescent field will be coming and you can tap a bit of light. And from there, it is shown here, beam splitter actually can copy a pulse, and if it sees that some intensity is reduced, he can actually amplify that one. So this type of system he can install, and Bob will never come to know that someone stealing data here. And even though all the mathematical algorithm, if you use that things nowadays you can crack, if there's someone sitting here, he can crack the data, what is key can be decoded and can get data out. And they will not be knowing at all. So this is the problem. This is the loophole in the communication system. So how this thing can be done? It's a very simple way I try to mention here, explain here. Suppose you think that this one polarization state coming here, and this is the detection system at the Bob site. That means here, Bob is this state is sent by Alice and Bob is receiving, and he is using two detector, so measuring the probability. And Alice can randomly change this theta value, and he also can randomly change the theta value, measurement system here, and they can separately, classically they communicate their data, but they will not reveal what position they are measuring. But looking into the data, they can find which data other side is correctly matching. That means angle setting from Alice's side and angle setting in Bob's side, that can be understood by sharing the result. Okay, result sharing only you can say that what is the angle Alice's side is used. And that particular point when it is matching, those bits they will be using as a key. And those keys they can actually multiply into the actual data when they are sending. So those keys only will be known by Alice and Bob. In between, if anyone, for example, if trying to measure in between, try to measure, suppose it is single photon coming, for example. If actually trying to tap that photon and take the data and to deceive Bob can send another photon. But problem is that when you measure here, like this type of setup D1 and D2, you are measuring only horizontal and vertical. You don't know, you will never be, it is hardly possible to get what is the theta position because he is not getting the data from Alice, data. So when he try to send another photon to Bob, it will be sent with a different angle. So when Alice and Bob sharing their result, that time if there certain amount of data should be matched. That is the rule. If it is not matching, they will understand that okay, someone is actually cheating in between. Someone actually dropping. That time, that channel, they will be actually stopped. They will leave that channel and they will re-establish the channel. As long as they are not getting the correct number of data stream bit, they will be leaving that channel. Okay, in this way you can secure. At least you will be knowing that someone is cheating here because your data, what you supposed to get here, number of correct data, you are not getting because theta is changed now. Okay, so that is how security is established. Actually, it is actually nowadays people already started using, implementing, and available devices are available. And then next thing is the qubit. Quantum qubit. You know bit, that classically bit is a bit has a two state, 0 or 1 binary state. And that Boolean algebra you use and all the computational things, everything they are using this 1, 0 bits. Okay, but here quantum bits are being used. How? That is quantum bit is, you can have a photon, and photon also you can think of two state. Maybe horizontal polarization one state and vertical polarization one state. You can imagine horizontal polarization is 0 state and vertical polarization is 1 state. It is something like that. High voltage is 1 and low voltage is 0. Here also horizontal polarization you can consider 0 and vertical polarization is 1. That is the two state of a photon you can imagine. But you know, earlier we have discussed, you can actually express that superposition of states also. Different coefficient you can just add, and then you can superimpose these two eigenstate to get another pure state. So that pure state, how you can define, you can think of something like this in a Poincare. This is actually called, it is actually Poincare sphere, but later on actually Felix Bloch, he is a student of Heisenberg, PhD student of Heisenberg. So he actually, like psi is starting from origin and reaching here, in the sphere, ending in the sphere surface. And that psi can be defined by cos theta by 2, 0 state, or j phi, 1 state. This kind of superposition you can think of. So you can vary theta you can vary from 0 to pi, and phi you can vary 0 to 2 pi, and it need not be discretized. Any function, any theta, any phi you can consider. So you can actually generate huge, gigantic amount of states, psi, infinite number of pure state you can generate. Okay, from just single photon, horizontal polarization 0, vertical polarization 1. Now in between all the states you can generate, as long as you can change this theta value and phi value. they can be done with optical devices, photonics devices. And then you can get huge states you can generate. Where the classical state, classical bit, actually you have only 2 bit, 0 and 1. And here you can have infinite number of states you can generate. A single qubit. Single qubit, you can have infinite number of output. Okay? So that infinite number of output you can utilize for your computation purpose. So here just pictorially it is shown here. Suppose you have a quantum logic gate. Quantum logic gate is nothing but classical photonics devices. Okay? They will be just using just to manipulate this theta value and phi value. Okay? Just to manipulate the states. So you can think of Q1, Q2, Q3, there are n number of photon, n different photon, n different qubit. They have 1, 0 and then superposition states. You can prepare them as per your wish from your output side. And all the qubit, you can actually simultaneously, you can, if you have an n input port and n output port, you can just feed here and only a single process state, you can actually change all the states and you can get output qubits. So you can just parallelize these things, okay, and you can get a measurement. So the beauty of this quantum computation is that you are using quantum state so that you can actually parallelly, you can use infinite number of states. You can orient infinite number of states. This quantum logic circuit, it is a simple photonic circuit. You can just control it by common electronic circuit like field programming, FPGA, field programming gate array, which is normally used in quantum normal microprocessor. That thing you can control and you can get it output here. So this is how actually quantum bit, entangled photon pair or single photon can be used for quantum key distribution and quantum computation. Okay. So this is all these fundamental things. You will learn many more things in the next presentation from Anant Jha and Shyamal from Canada. I'll just go how the integrated part is coming out. Prajush, I have how much time left?
Okay, you continue, no problem.
Okay, I think everything going smooth, right?
Yeah.
Probably I'm going a little bit faster, but I will try to slow down. Okay, so I have 11 slides more. Okay.
It's fine.
Okay. You see, all the things are so far good. So basic thing understood that we can generate basically a single photon, entangled photon. We can manipulate also by classical devices. So next thing is that how to integrate them together. Like IC, integrated circuit, microprocessor, what you see inside your mobile phone or inside your computer, laptop, etc. That type of chip, how to make that. That is actually industrial, but that is actually the ultimate thing for making things to work. So here I just try to show you how, if you just break your electronic IC, you will get something like this. Okay, so you see there is a silicon chip. That's a microprocessor, can be memory or anything else there will be there. There is a billions of transistors you can integrate together, nanoscale devices. And that technology is there. You cannot rule out that technology. It will continue to, it cannot be replaced, I guess. Okay. And then you have output pins are there. That is there are 14 pins normally in the IC 741 op-amp. If you have used also, there 14 pins will be there. And all these pins, you know, where is the bias and where is the signal, all those type of things, you know, those type of things. But inside, you can imagine there will be hundreds and billions of transistors and they are connected each other. How they are connected? Because they are actually, you can consider they are digital devices. That means logic circuits are there. There's one output from one logic get to another logic circuit if you are just giving. So you need some kind of data transmission, means high-low transmission need. That means pulse transmission needed. You need a transmission line inside. That means inside there is a transmission line already. In this electronic chip, there are transmission line. So if it is, you are thinking that it is 1 centimeter by 1 centimeter chip, this one, inside, if you have billions of transistors, you can think of kilometers, thousands of kilometers, transmission lines also there, but they are so small inside. You can't imagine. Someone is saying that you can actually stretch them up to the, if a normal modern microprocessor, all the transmission line they use, you can actually stretch them up to the moon or even up to the longer distance or so. So that type of transmission length required, and when they are sinking because of the technology, you are packing more and more transistor, they have a bandwidth limitation. So, and that is one thing. And also another thing is that if you are packing them together, billions of transistors, you are packing them, they will generate heat. And because of the heat, actually performance degrades. So that's why people are nowadays using multi-core system. All the cores are segregated. 3-4 cores, multi-core, even people are talking about GPU unit, thousands cores are there, all those type of things. And that's core to core. Again, if you use that kind of copper line, transmission line, that is a bandwidth limited, frequency limited, bandwidth limited, high speed operation cannot be possible. So what people are doing, okay, as long as your electronic transmission line shorter distance up to millimeter length, it is okay. More than that, I think if you replace this transmission line, electrical interconnect to optical interconnect, that means electrical signal you need to convert into optical multiplex, and you can first bandwidth, you can enjoy the bandwidth and convert back to the electrical signal, and then you can decode the data and can feed into the next core. So within the chip also you can have an optical interconnect, and chip to chip, core to core, rack to rack, all those type of things can be done. You know that this optical communication also works in the same fashion. You have a transmitter, you have a receiver in between fiber line. But that is a long haul communication success. But whenever coming down to the chip level, technology needs to be supported. Source, detector, modulator, multiplexer, demultiplexer, filters, all those type of things, you have to pack them together. So you need an entire lot of photonics technology. And that photonics technology, if it is coming from some foreign technology other than your silicon technology, it's a problem for interfacing. So people tried to integrate them. If inside silicon itself, your electronics and your photonics can be integrated together. Okay, so that is how people tried. For the moment, same technology they use. Here it is currently, normally this type of packaged device people are using. One is actually, you see that here a vertical electronic integration. Here electronics are there. In the bottom there is a silicon photonics integrated circuit is there. Where bonding will be there, they will be mounted. And silicon laser cannot be integrated. Indirect bandgap semiconductor, high-bit laser will be integrated here. And then they will be packaged like this. They will be mounted in a thermoelectric cooler to control the temperature. And then hermetically they can be sealed, cased. And you will be getting outside in and fiber output. So that is how normally photonic integrated circuit. Now it is commercialized. Now you have the product that this unit actually directly you can plug in your laptop computer. So that optical you can connect directly to the fiber. Okay. So this is one of the example here. Recently I just found this March-April news. I saw that Terafy technology. That's IR Labs with the collaboration with Intel. They actually demonstrated such a transmitter. This is the board if you see here. So here in the same chip, actually this high-speed optical interconnect they integrated along with the electronics. It's the same technology, 45 nanometer CMOS technology they have used, and they have integrated so many transmitters and multiplexer, demultiplexer, and they could actually communicate one chip to another chip, one card to another card, 1 terabit per second data stream, and their target is 100 terabit per second. So they have just launched recently. This type of transceiver is available now in the market, which can offer 1 terabit per second. So if this type of transmitter comes, I think you can imagine that nowadays I think we see frequent interruption also happening other time for the presentation, stopping, etc. So those things will go actually completely. Yes. So how it works? I just tried to give one example here. You have a clock distribution here, chip 1 and chip 2. You want to communicate between these two chips. And you have off-chip laser, you can put somewhere some frequency comb lasers are nowadays available, emitting multiple wavelengths. And these are the ring. Here it is on 5 rings are there. So you have 5 different lambda, different laser wavelength. You can launch here. Okay? And then these lambda, different lambda, they can be separated with 1 nanometer spacings. One is 50 nanometer, maybe another one 51 nanometer, and so on. And those wavelengths are resonant to this ring. 5 different rings. So normal situation, what you would see, all these lambdas, they will be actually stored inside the ring. Some energy will be stored. And that will be missing in the transmission. But depending on your digital clock here, digital data, it will actually modulate the phase, ring, individual ring separately. Okay, the different channels, different data stream will come. And each of this lambda 1, they will be modulated with they can be same speed but different data stream. And they will be loaded in the same waveguide. And you can take them into fiber, modulated output, and take to chip 2 here. Okay, and chip 2 you can couple here into the another chip. And here, same set of ring resonator you are using. And the lambda 1, which is resonant to this ring, that will be dropping here. And you can put a photo detector. You can tap a little bit of light and you can detect it. So all this 5 lambda, you can actually drop here and you can, all the data you can recover and clock data, everything you can recover, you can process that. So that is one of the chip it is actually shown. You see this input output fibers are there. It is a ribbon fiber. It is not like a standard fiber what you see here. So maybe hundreds of fiber you can actually just clap together here. It's like a ribbon. And you can just, this type of jack is there. You can just put, insert it is like a USB drive. And then you can get this chip connected to electronics actually. Okay. So they are actually targeting 100 terabit per second, 10x better than what is the present things. Okay. Now, so what I say that quantum key distribution is possible also. So now this, I think I see that Kiang et al. Recent Nature Photonics 2018, not very recent. They actually demonstrated this normal CMOS technology, whatever being used for other transceiver I have shown here. They have used that laser source, laser pulse, they just a single photon pulse they are pumping here, they are launching here, photon source here, and then you can actually control the phase and you can make, because of the delay, you can decompose that into 2 pulses. Okay, because of the delay. One thing is that you can say that one coming through the longer path and another will be coming in the shorter path. So one will be coming earlier, another will be coming later. So these 2 states also you can consider they can be also entangled. That is called energy, that is energy time entanglement, is called path entanglement. So that thing also, this each of these pulse or photons, you can say that you can also code with a different phase. That's the data basically. And the data, again, you can just transmit and in the receiver it comes and you can decode by controlling the, instead of polarization you are controlling here phase and here also phase, random phase they are considering and here random phase considering and detection data they are sharing and they were finding which set of data actually they have a similar type of settings. And that will be the key basically. Part of that they will be using as a key. Okay, that is chip level already demonstrated, QKD purpose. That's all in silicon photonics technology. And that is to existing CMOS technology that can be fabricated in CMOS foundry basically. And this is another example of linear optical quantum computing. While linear, you are using qubit and all the unitary matrices for all the logic gates. I said that for quantum process, quantum logic gate, they are basically Mach Zehnder interferometer and delay lines. Okay, and you can actually design different type of logic circuits, and that logic circuits can be also driven by a normal FPGA. That's a normal field programming gate array. Normally, that is well-known circuit board you can use, and then you can get a particular type of functions here. Here it is shown that there are 4. You see, there's a 4 different spiral thing. They are actually single photon generator. Single photon or entangled photon generator. They are long waveguide they are using so that you can efficiency you can improve. That normally this Chi3 process is very weak. So you need a longer distance even to generate even 1 photon in 1 picosecond, 1 nanosecond. You need to really design a very good waveguide source also. Okay. So this is the thing. Now I am coming. This is the state of the art. Very because if you see that this quantum computation, linear optical quantum computing QKD, I would say that if you just search every day we will be getting dozens of papers being published in Nature and PRL and Optics Express, all the Journal of Light Wave Technology. At least dozens of papers will be, you will find new paper is being published. So this is a hot topic, whole world actually, a lot of big labs, they are actually investing a lot of, I think I see something like that when transistor was discovered that time, all the big semiconductor giants, they invested a lot And that is how electronics industry actually moved forward. And now I see that now all giant, semiconductor giant, they are also investing money and a lot of research going on. And I think it is very soon we'll be getting optical photonic computer, I would say, quantum photonic computer. So now I come to what we are doing at Madras. A couple of slides I have just to explain. So you see, we have the technology, all the fabrication technology, whatever fabrication technology CMOS foundry can do in a larger scale, we can do the same thing smaller scale here for photonics device fabrication. In IIT Madras, our Center for MEMS and Nanophotonics. So it is just a biograph, just kind of cartoon here it is shown. It is the dream thing to achieve. That was actually published in Journal of Selected Topics in Quantum Electronics in 2016. This type of chip is actually, we want to fabricate completely in CMOS foundry. Okay, that is the goal for all quantum, those who are doing integrated quantum photonics. They are targeting that ultimately one day we will get this type of device. What is there inside the device? You just see all the components here. You need a photon source. That is first thing. And next important thing is that, you know, to generate this photon source, you need an intense pump. That pump laser, that is actually, once it is generated, once daughter photons are generated, that pumps are actually useless. If you keep that in the circuit, it will keep on creating noise and it will generate more photons here and there, and that will contaminate your entire circuit. So first thing what you have to do, you have to separate it from the pump. Whatever generated, you have to separate. Pump has to be suppressed completely, has to be thrown out completely. At least you need to suppress the residual pump at least 100 dB. Even if you have just 1 milliwatt pump is coming out, that 1 milliwatt pump, you have to, we consider that if it is 1 milliwatt coming out, if you can reduce it to 100 dB, you attenuate 100 dB, then only the number of photons in the pump pulse will be coming down to vacuum noise level. And this photon pair you are generating, they can be revealed. Actually, you can use them properly and you can detect them without any disturbance from pump. So this is a very important component, pump removal filters. And that is true, you need 100 dB filter. Till now, I think in the market it is not available, that a single stage filter can give you such a huge amount of extinction. Some noise will be there, something leaking, photon will be leaking. So that is a huge challenge. People are using this pump filter as an external. So because their detection, everything will be external. Externally, they will be filtering everything and then they will be detecting. So cascading different type of filters. Maybe 10 filters they are cascading and then just attenuating pump, and then they are extracting the photon for experimental purpose. But ultimately what you need photon source, good pump removal filters, passive and active devices, and then you need a single photon detectors. So single photon detectors, you can imagine, one photon will be hitting in your detector and you should be able to count that photon is coming. No noise, nothing, even dark also if you see, some photon will be coming here and there. So it's a very sensitive thing. You need a highly efficient single photon detector. And sensitivity, efficiency, everything should be very high. So present day, these single photon detectors people are using also off chip, because they are using superconducting nanowire. It's a kind of Josephson junction where when one photon is falling, because of quantum mechanical effect, you will see a large amount of current flow. So you can measure that current. So that is how it is done. Now in future, but I think that is the problem of that is that superconductor, superconductor means room temperature superconductor is not available. So you have to again bring it down to low temperature. That's the problem. So nowadays people also found the technology that type of photo detector, some people demonstrated also, can be integrated on chip here. So in that case, entire chip you have to again cool it down, but also some work is going on that some avalanche photodiode, SPAD, etc. they are using. So they are quite efficient also. So single photon detectors also, it is possible. It is at least lab level, people demonstrated. And then you need an electronic circuit together also, all these type of things. So far, what we have missing, this electronics is available, CMOS industry. And all these waveguide, ring resonators, Mach-Zehnder interferometers, phase shifters, all those type of things also you can fabricate. But the current device design, it's not giving really 100 dB extinction filter. That is one challenging issue. Another challenging issue is that photo detectors. Otherwise, these things are actually the hot topic. People are concentrating on that. So, and instead of this long spiraled waveguide that is about few centimeters long waveguide, okay, it's actually spiraled in micron dimension basically. So we could do one micro ring resonator. So if you launch here just resonator, you know, earlier people are using in transmitter, then pump wavelength goes, and if you just use this pump wavelength and match to one of the resonance, that field will be developed here, and then other resonances, neighboring resonances, your signal idler daughters will be generated, and that can be coming out. Okay, so in that case you can get your signal and idler photon along with some kind of pump. And using this type of ring resonator, one added advantage is that since pump wavelength is actually resonant to this resonator, so it will be stored a bit here. So the pump laser, it will not go directly, whatever residual power, it will be a little bit attenuated also. But after that also you need at least 100 dB or more. So in principle it would be ideal if it is 120 dB. 100 dB extinction filter you need to reject the pump, just eliminate pump. That is a vital thing to extract the entangled photon pairs or detectable entangled photon pairs. So we are working on this two front, this photon source and this pump removal filter at this part. And all other things we have demonstrated, and once we can implement here successfully, then we can go for larger scale circuit level research. Okay, so one of our recently we have demonstrated, so far people demonstrated earlier 30 dB, maybe 35 dB on chip filter, and outside they were actually cascading 100 dB extinction. Very recently we have designed a special type of DBS structure, and that DBS structure is giving actually, you see certain range of wavelength it is dropping. You see just reference waveguide, if you see this level of this DBR is also, if you also test a little bit higher pump power level, we found that extinction, when it is in the pass band pump, it is going about 3.5 dB input here, power transmitted output, but when going through here, that power, it is down to about -60 dB. So it is more than 60 dB extinction we could achieve. That thing, that is very, very encouraging, and we presented. He's supposed to go to USA during the conference, but because of this COVID pandemic and this online conference, he presented recently here, and that is a very just a record results basically. Your pump wavelength is not matching exactly to the resonance wavelength. You can tune a bit, and also you can tune a bit also of your signal and idler wavelength. So this is actually reconfigurable type of device. You can fabricate. That is actually very important, so-called photonic programming, photonic gate array, FPGA. It is an analog of electronics things. That is also will be useful if you can control this. You can reconfigure this ring resonator, and you can switch all those type of things. This is a latest technology coming up. Here, this is a integrated quantum photonics. Is really it's now reality today. I think what I have played because of the pandemic situation, etc. It is announced, budget not allocated yet, but at least announced, and we are waiting for that to have big lab facilities and big research outcome. And for students, I would say that it's a huge opportunity, and it's a hot area. And now I think in this area, if you come for research, I think a job is there actually. I think all the students, my students graduating here, and they are before graduating they are getting placed. Even PhD students also, they are getting placed. And sometimes I'm happy to tell that some companies, some people, they are communicating me that if you have graduating student or graduating maybe next 2-3 months, tell me, we want to actually hire. So that is not because that I am teaching them very nicely or they are very good or something like that, because this technology is so hot probably the trained people, they want to go forward. Maybe that is my humble submission. But anyway, I think this is a hot topic. And for students' perspective, I say that if you want to know a little more about our research, you can also go to our website. At our website also, this is my research group. And whatever this filters and quantum photonics entanglement being done, I think this guy, this is Arnab Goswami, not that Republic Arnab Goswami. Is one of our bright PhD student. He's from Bengal also, and he is actually. I must confess that I have learned a lot of things from him also, because he's forcing me also to study quantum photonics, and whatever I learned and whatever I presented here, I think that his contribution is there. And another guy also, he is very nice, Ram Mohan. He's also, they are actually complementing each other. Both are very nice students and doing good research. And all other people are actually, they are also learning and they are contributing. Their different area, RF area also is there. But the technology being same, they are actually discussing each other. And same type of device, only concept is different. We are actually regularly having Google Meet meeting also every day. We are having 1 to 2 hours Google meeting. We are discussing and things like that. So I feel comfortable also. If you have some kind of questions, you can feel free to ask me. I will try to answer. Otherwise, you can mail you, as Bijoy said. So with this, I thank you very much. I thank you actually because without any interruption, presentation went well, I hope. I'm not sure whether I'm very fast or not, whether audience could follow me a bit or not. I tried my level best. But okay, with this, I just hand over to Pius.
Okay. Thank you, Professor Das, for such an energetic and informative lecture. Actually, this lecture summarized the last, summarized the last 2 lectures in the lecture series 1 discussed by Professor Ghatak and Lognathan. You started with the origin of quantum theory, Planck's works, photoelectric effect, then moving over to the harmonic oscillators, vacuum energy fluctuations, etc.
So, do you see some overlap? Do you see some overlap with Professor Ghatak's talk, or?
Actually, both are from the fundamentals view.
Yeah, but different aspect probably, I guess.
And then you started with the fundamentals of this photonic beats, quantum entanglement, photon pairs, single photon quantum states, etc., which are of highly interesting in the present research. Mostly the quantum computing is, I think, the most emerging field nowadays worldwide. And you have already mentioned that already a huge amount of funding has been allotted for this purpose.
Yeah,
so I think this lecture is very inspiring to all the students and also to the researchers who are really thinking to work towards the quantum computation and quantum photonics devices and integrated optics. So now the session is open for discussions. Participants, if you have any questions, you can put in the chat box. Already I have collected some questions from the chat box. One is from Pritam Bhakat. Pritam, are you here? The question is, what is the difference between the two processes, SPDC and SFWM?
Okay. So, I think I have just tried to give you this thing. I can go back to that one. Yeah. So, you see, I think I don't have that slide. I think if you follow that, Professor, I can refer Professor Bhadra's slide. He was explaining that nonlinear polarization. There will be Chi2. Chi1 is a linear process, and Chi2 is actually second order nonlinearity and third order nonlinearity. All these type of things are there. So whenever some pump electric field is there, and in presence of Chi2, so what happens that nonlinearity play a role. So you can actually multi-frequency will be generated. So one of the option is that this palm photon, they will be interacting. 3 wave can be interacted. 3 electric field can be interacted and their frequency can be different. So one of the frequency, if it is pump that is supplied, 2 other frequency will be generated automatically. And that is actually called spontaneous parametric down conversion. So it's a parametric is a historical name. It is why it is called parametric, I don't know. It's just called parametric means it's depending on the pump frequency, actually you can control the signal and idle. It's a spontaneous process for sure. That is because of the vacuum pressure. Now in case of Chi3, the material is such that the Chi3 component is dominant, for example. Chi2 is not there. Nonlinear because of this, because of all these tensor things, symmetry, etc. all play a role. So because of the presence of Chi3, what happens? It's a 4 electric field will interact each other. Out of this 4 electric field, because of the Chi3 process, out of these 4 electric fields, 2 electric field components can come from pump itself. And 2 other will be generated, one signal and a idler. So 2 pump photons will be combined together to produce 2 different daughter photons, signal and idler. And in this case, it is called spontaneous 4-wave mixing. It's a 4-wave mixing, 4-wave, 2 pump photons and 2 signals and idler. So 4 waves, they are mixing. You can actually reshuffle them. You can just pump signal and you can generate other frequencies also. Depending on the situation, phase matching condition, etc., you can actually create. A lot of engineering needed there. Okay, so this is called actually spontaneous 4-wave mixing process is the light matter interaction due to the Chi3 process. And spontaneous parametric down conversion due to the Chi2 process. I hope I could explain.
Yeah. Okay, the next question is from Priyanka Verma. How we differentiate entanglement photon pair from classical photon? How
you actually classical photon meaning as I said that I think this slide would be sufficient. So ultimately if you have single photon, then if you know its polarization, then that is usable, no doubt about it. But as I said that classical wave, classical photon, that is maybe thermal, super Poissonian or Poissonian laser source, I said that it is extremely difficult to single out a photon because they are bunching together. Sometimes comes all together and sometimes maybe nothing is there. You cannot find a photon on demand. So that is how classical photons you cannot single out. Okay, but in case of entangled photon pair, you know that okay, if at all it is generating, and if you can detect one photon, then you can you are definitely sure that one heralded photon will be there for your use. So you can have a timestamp. At this point of time, I detected this one. So at this point of time, that photons are available and that can be used for some logic operations. So that is how it is differentiating. So normal photon, you cannot actually, you cannot isolate single, you cannot create a single photon from laser source. Single photon means at a time you should have a one finite photon and that time no other photon will be there.
Okay.
So single photon source means not that only one photon it will be emitting and stop. It is not that. It will just keep on emitting, but the photons will be well separated so that you can detect separately. Okay, fine.
Okay. One more question. What is the phase relationship between the 2 entangled photon, singular and idler?
Yes, I think that's a good question because if I say this thing, I think I am just considering only energy conservation here. Okay, assuming that the momentum is conserved already. Okay, so normally if you say in Chi2 process, so momentum conservation means you need to consider about K value, wave vector, right? And wave vector is associated with the refractive index. Okay, so refractive index, if you see, when palm photon dissociated into 2 smaller photons, omega s and omega I, smaller, that means energy is smaller, wavelength is longer, right? So that longer wavelength and palm photon is a shorter wavelength. If they are traveling because of the dispersion, they will travel with different phase velocity. So that means they will not be phase matched. That means you can imagine one photon generated here, and for the same wave generating another point here, if pump and those daughter photons not traveling together with the same phase velocity, they will walk away and they will interfere, they will destroy. So that is the problem. But you have to have some kind of engineering so that some kind of grating type structure, that's kind of lithium niobate people use normally Ki2 material, periodic polling they do, so phase reversal they do, ferroelectric domain reversal, and they actually manage quasi-phase matching process so that you get build up things. But in case of Ki3 process, it is a little bit easier. Why, you know? Because here two photons are there. In case of silicon, two photons together creating two other photons. You see, two photons creating two other photons. So that means their wavelength and frequency, they are not far away. So they are not much dispersive. They can travel closer. But you can design also waveguide that dispersion can be zero. Dispersionless waveguide you can also design for a certain wavelength window. So phase matching condition can be fulfilled. So they can travel. That's a good question anyway. Thank you.
Okay. And one more question from Vishwajit Maiti. Sir, how the quantum interpretation using 0 and 1?
Yes. That's again a good question. I thought I could explain. So you see, here you can consider the photon, right, with a theta polarization. I think you will be able to explain here. So something, this is somehow you are detecting with a D1 detector and D2 detector. You have a polarization beam splitter, right? So this photon, when it is falling, I know that some probability is there that you can have some kind of horizontal sin theta probability will be here and cos theta probability will be here. So when it is transmitting through this beam splitter, the polarization of that photon will be vertical. It was theta, but when it is transmitting, due to this type of interaction here, whatever reason it is there, the photon is completely transmitting, but its polarization is rotated. It's vertical. But occasionally it can happen also that this entire photon, it is coming here. In horizontal. This is vertical and this is horizontal. So a photon you can actually see either in vertical polarization or in horizontal polarization. If you define, for example, in classically, 1, 0 means what? You have whenever high voltage or higher current flowing, then you can consider it is 1. Lower current is 0. So it is a definition. 0 means what is 0? 0 is absolutely not possible actually. Some noise level will be there. Only high level you consider 1 and low level you consider 0. Here also you can consider one polarization as 0, another polarization is 1. So this is the two state. And then you can again superimpose. Then you can get all the quantum states, pure states you can get. That is the beauty here. But classically you have either 0 or 1, either high or low. But here all the quantum state you can actually create and you can process them and you can measure them also. So that is the beauty here. That is how quantum bit and classical bit is differentiate. Okay?
Okay, one final question is there from Arnav Jana. Sir, what is the neuromorphic computation?
Yeah, that is actually, I think this is a hot topic, but I don't dare to explain anything on that because it is something neuromorphic means I would say that it is some kind of artificial intelligence type of memory type application is there. So you can, if you can just consider some kind of memory effect, just like a normal memory in the computer you use, people are mimicking some kind of circuit operation with photons also, so that you can actually mimic what your brain can do also. Normally your brain, because you know whatever things we have done long back, that is actually stored in my memory, and suddenly if some situation comes and I need to take some decision, all the memory process itself inside our brain and help us to take a certain kind of decision. That decision may be wrong decision or something. But that is all biochemical reaction happens, and that memory effect, that all type of processing happens in the brain. Similar type of things people are trying to mimic in the chip level, so that you can actually use them in a robot or something like that. So artificial intelligence, so human being can be little bit can be replaced by such things, and all the machine type of things can be automation, everything can be done. That much I know, and one of my colleague is working also in that area, and he believed that this silicon photonics, our type of research, will be helpful for them. And we have a plan to meet for some discussion. And we know some research also going on. PRABHAT also in Italy, they have certain kind of research. I have seen some of the papers, but up to this point, I can explain. I don't know much more than that.
Okay. Thank you, Professor Das, for your energetic deliberation, and we are really greatly benefited from your lecture. And we hope after this corona pandemic is when it will be over, then when you will be visiting your hometown, obviously we will be having you in our college and delivering more on this quantum computing, quantum photonics.
Yeah, thank you very much. Thank you very much for this opportunity. I actually enjoyed a lot interacting with you, and good questions also, of course. Yes. I never expected that such a good question will come up. It's very good. I'm happy that people are also up to date. And
we must congratulate also the participants for their presence here and for their support.
Yes. I think that is important.
That is very much important, because today we faced a lot of technical problems over here, but the participants are patiently waiting for the lectures till it's around 7 p.m. It's quite long, starting from 3 to 7 p.m. It's really very amazing that the participants are waiting for this lecture. So, on behalf of the organizing committee, I must thank Professor Das for his deliberation. I would like to thank Honorable President and all the members of the governing body of PRABHAT Kumar College, CONTAI, and the principal of PRABHAT Kumar College, CONTAI, for their permission and various kind of cooperation for organizing this online webinar in this pandemic period. So I want to thank, on behalf of the organizer, the entire team member associated with this webinar, and my dear colleagues supporting this endeavor from different ways. And thanks to all the participants for attending this webinar and making it a grand success. And we see you all on the third series of this lecture that will also be held on 13th of July. So thank you all for your patience, and thank you very much. So with this, I conclude this today's lecture session. Thank you all.
Thank you very much. Thank you very much.
Thank you, and stay home and stay safe.
Stay safe, yeah. Thank you.